For those of you enrolled in Conceptual Physics AB, this is the lecture on standing waves. For those of you enrolled in Physics AB and in Honors Physics AB, this is part one of that lecture. In my previous video, I demonstrated standing waves for you. As we'll see in this lecture, there are some simple mathematical patterns that arise when describing standing waves. Standing waves is a specific type of interference pattern. Okay, so as I just said, it's a specific interference pattern. And in this lecture, we want to run through the basic mathematics of those patterns. Okay, now let me begin by drawing out some coordinate axes, like so. Okay, the spring itself will be placed along the x-axis, that is, and then perpendicular to that, the y-axis, this will be the displacement from the equilibrium position. Okay, we stretch out the spring like so. The spring has a length L associated with it. And then I form the first of my standing waves, which, if you recall from my demonstration, looked like this. So once again, here's the x-axis, here's the y-axis, and then the spring looks like so. Okay, this particular interference pattern is formed by me, for example, transmitting simple periodic waves in this direction. They then reflect at the closed end back in the opposite direction. The reflections are pi radians out of phase with respect to the incident waves. The waves superimpose or interfere to produce this interference pattern. Okay, now half of a period later, the standing wave oscillates to here, and once again, this is the space L. Okay, now take a look at this diagram. In this space, how much of a wavelength is present? Well, a full wavelength would look like this. So then therefore, notice in the space L that I have here 1/2 of a wavelength. Okay, now take a look at the next of the standing waves. Once again, a simple diagram like so. That is like this in the space L, and then half a period later, it oscillates to here. Okay, how much of a wavelength is contained within the space L? You'll notice, of course, that it's a full wavelength. So then therefore, in the space L, I'm going to write it as 2/2 lambda. And when I write down the next standing wave, you'll get the idea fairly quickly. That is, of the pattern that is being picked up here. Once again, the y-axis perpendicular to the spring. The spring is along the x-axis, and then the next standing wave looked like this. Like so, where once again, this is the space L, and then half a period later, it oscillated to here. Okay, in the space L, you'll notice there's 1.5 wavelengths, which I'll write as 3/2 lambda, and so on and so on and so on. So very quickly, we see a simple pattern here associated with the wavelength associated with these standing waves and the space L. We can easily write that pattern in the following manner. In the space L, we have to have a multiple of half wavelengths. The letter N is referred to as an integer multiplier. So for example, on the comp board, the first of my standing waves here obviously is n is equal to 1. This is n is equal to 2. This is n is equal to 3, and so on. Now, in addition to there being a pattern between the space L and the wavelength, there's also a pattern associated with the frequencies as well. Here's how the frequencies come in. Okay, recall from basic wave kinematics, simple periodic waves, that the speeds of these waves is equal to the wavelength multiplied by the frequency. Okay, divide the wavelength lambda to the other side to write the frequency as v over lambda. And now from this expression here, the wavelength lambda is 2L over n. Let's go ahead and plug that here into the denominator of the expression. Like so. And then if we rearrange it slightly, let's move the n up to the numerator, we then end up with this expression here. this expression here describes the pattern associated with the frequencies. So for example, on the top board, when n is equal to 1, the frequency is the quantity V over 2L. This particular frequency is given a name. It's referred to as the fundamental frequency. It's also referred to as the first harmonic frequency. So this is the fundamental or first harmonic frequency. Okay, and then right over here is n is equal to 2. When n is equal to 2, this frequency here is twice the fundamental frequency. It's the quantity 2V over 2L. When I was demonstrating this with the springs outside in my previous video, I specifically said that I was going to double the frequency of my hand from here to here. The reason why I did is because this harmonic frequency is twice the fundamental. This is referred to as the second harmonic frequency. It's also sometimes called the first overtone. Notice what's starting to creep into this description are terms associated with music, harmonics, overtones, and so on. Ultimately, scales, octaves, and so on, upon musical notes and so forth are built, are dependent upon multiples of the fundamental frequency. I'm not going to go through all those specifics here, but suffice it to say the mathematical patterns associated with scales, octaves, and so on begins here with this description of standing waves. So once again, this frequency here is called the second harmonic frequency. It's also sometimes referred to as the first overtone. And then this right here, my last example, this frequency here is 3V over 2L. And 3V over 2L is 3 times the fundamental frequency. This then therefore is the third harmonic frequency. It's also sometimes called the second overtone, and so on and so on. So literally by just looking at the standing waves, we can easily discern what these patterns are for the space L and also for the harmonic frequencies. Okay, there are a couple of definitions associated with standing waves that I want to briefly mention before we take a look at a simple example. Okay, let me do a little bit of erasing here. Okay, take a look at n is equal to 1, for example. We have these 2 points right here, the boundaries, if you will, of the spring that are motionless. These 2 points are referred to as nodes. On my other simple diagrams, there are 3 nodes here for the n equals 2 standing wave. There are 1, 2, 3, 4 nodes here for the n equals 3 standing wave. Notice that the number of nodes is always 1 more than the integer multiplier. So when n is equal to 1, you have 2 nodes. When n is equal to 2, you have 3 nodes. When n is equal to 3, you have 4 nodes, and so on. But then we also have these points here, here and here, here and here and here, and so on. These points here are the points of maximum displacement from the equilibrium position. They're referred to as antinodes. Notice that the number of antinodes matches up with what the value of the integer multiplier is. So when you say n is equal to 1, you're specifically saying 1 antinode. When n is equal to 2, there's 2 antinodes. When n is equal to 3, there are 3 antinodes, and so on. Notice that all of the nodes, by the way, are separated from each other by a half wavelength. That's the case here and here, 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 and here, and so on. And the antinodes are also separated from each other by a half wavelength. So from crest to trough, for example, here, crest to trough here, and so on. So the antinodes are separated by a distance of a half wavelength, as are the nodes. Okay, let's go ahead and take a look at a simple example that just briefly illustrates these patterns. So copy the example down into your notes as I read it here. Okay, the guitar string is 0.7 meters long. It's plucked such that the string vibrates at the fundamental frequency of 320 hertz. I'll explain this in greater detail when we eventually get to musical instruments, but when you do pluck a guitar string, for example, you are specifically playing the n is equal to 1 standing wave. Okay, what is the wavelength, period, and wave speed for parts A, B, and C of the problem? Okay, so let me go ahead and erase portions here of the board that I don't need for parts A through C of this problem. We just need the n is equal to 1 standing wave thus far for this problem. What we're given is as follows. The guitar string is 0.7 meters long. That's the length L. Okay, it's plucked such that it vibrates at its fundamental frequency of 320 hertz. Okay, in part A of the problem, we're asked to calculate the wavelength. Specifically, this is for the n is equal to 1 standing wave, where in the space L, we have 1/2 lambda, 1/2 of a wavelength. So then therefore cross multiply the 2 here to the other side. So the wavelength is 2 times L, it's 1.4 meters. So you can't see the entire wavelength when you're taking a look at these n equals 1 standing wave. The entire wavelength would look like this. We can only see half of it, however, in the space L. Okay, part B, calculate the period. Well, once again, frequency and period are just inverses of each other. So then therefore, if we cross multiply, the period is equal to 1 over the frequency. So then therefore, if the frequency is 320 hertz, then the period is going to be quite small. So let me just go ahead and calculate this as a decimal on my calculator. So 1 divided by 320 comes out to be 0.003 and change hertz, or seconds, excuse me, when talking about time, when talking about the period. So the period is quite short. The reason why the period is so small and the frequency is so high for a guitar string is because you place it under an enormous amount of tension by means, for example, of the guitar pegs. Okay, there's a little bit more to this problem here. We have part C. Okay, part C is asking for the wave speed. So let's just go ahead and calculate the wave speed as wavelength multiplied by frequency. So the wavelength, remember, was 1.4 meters, and then multiply it by the frequency here of 320 hertz. So 1.4 times 320, and you end up with a really large number. The speeds of waves on guitar strings are typically very high. In this case, it's 448 meters per second. Okay, let me move my file. Okay, and then lastly, in part D of the problem, we're taking a look at the frequencies of the first 2 overtones. So this is where the terminology comes into play a little bit. The first overtone is the same thing as the second fundamental frequency. So the first overtone, that frequency is going to be 2 times the fundamental frequency, the quantity V over 2L, which was given to us numerically in this problem, remember, as 320 hertz. So then therefore, this is 640 hertz. Similarly, for the next overtone, the second overtone, the second overtone is the third harmonic frequency. That's 3 times the fundamental. So then therefore it's 3 times 320 hertz, which is equal to 960 hertz. So these simple pattern expressions here associated with standing waves are easy to describe. Eventually this all carries over later, specifically when we start to describe musical instruments. For those of you enrolled in Physics AB and in Honors Physics AB, Part 2 of this lecture takes us through the trigonometry, which mathematically predicts these simple pattern equations.